So first of all, for OneSpin Solutions, so Sergio Marchese, got it right? Forgive me. So technical marketing manager at OneSpin. This is around the areas of front-end hardware.
Yep. Is it working? No. We have been having a few problems with it. Let me just check it. Have we switched on? After that.
Hi everyone. So I'm gonna talk about trust issues with in hardware. I'm not sure. You guys are familiar with RTL or more software? Guys. Usa RTL here. Okay, so because it's kind of I guess I need this for the yeah. So because I mean trust issues are, or let's say security issues, security vulnerabilities have the past mostly been associated with software, but hardware is gaining more and more prominence in this concern, let's say.
No.
Yeah, switch off, and it works. So I see integrity. One slide on OneSpin. So OneSpin is an EDA company, and our focus is on integrated circuit integrity. What we mean by integrity is really based on three pillars: functional correctness, when you look for bugs, for connect case, for example, where your hardware doesn't behave as it should. Safety. How your hardware behaves in the presence of faults, for example, random faults in the field. And this, of course, particularly important for applications like automotive applications, being compliant to standards like DO254 for avionics, ISO 62662 for automotive. And trust and security, where you're really looking for vulnerabilities in your hardware. And this is really the focus of this talk. So I'm going to talk a little bit about hardware vulnerabilities, malicious insertion during IC design, and trust assurance detection of Trojans. So this is a slide from DARPA. And if you look at the problem of malicious insertions and assurance of the supply chain, is a huge problem. You can have all stages that are vulnerable. You have all stages that are vulnerable. You can have even, they found lots of counterfeit parts into US military systems. And you can have malicious insertion during the production step. And you can have malicious insertion also during the design step. So, for example, you use an IP in your system on chip, and hopefully it does what it says on the tin, and nothing else. But how can you be sure? So if we look at security in hardware, we can see from the Wilson Research group study, Harry Foster, that I talked about this a lot, but in a different context. But if we look at security features, we have loads of ASIC projects with security features, loads of FPGA projects with security features. Really, security is important for more and more applications. It really is not only an issue with software, but also with hardware more and more. So another slide from DARPA. This is some data from 2015, a little bit old, but still relevant. So they saw that of all the vulnerabilities recorded in this database, CVE, quite a good chunk were also relating to hardware. Now, if we look at what happened in 2018-19, these have been very good years for hardware, setting center stage into security issues with the meltdown, shadow, zombie load, MDS. So all hardware-based attacks that could be used, for example, to leak secret information that are related to microarchitectural features of processors in this case. So I mean, we can see how hardware is becoming more and more important for overall system security. And actually, for DARPA has actually they have lots of programs. One of them is also looking at how to use hardware also to prevent security vulnerabilities. So also taking an active role beyond what is already done today, which is very confined, to prevent security vulnerabilities. So we have, in a sense, two issues. One is making sure there are no vulnerabilities in the hardware. And secondly, perhaps also use hardware security mechanisms, more advanced hardware security mechanisms. So if we look at in terms of, let's say, users, if we look at functional correctness, really it's about does the IC what it's supposed to do. And if you produce an IC, these are your customers, they want the IC to work. If you look at safety, the question is really, does the IC behaves according to the standard in the presence of faults, which can corrupt the normal functionality of the IC, random faults, effects. So it's a lot about understanding, for example, if the IC is tolerant to faults, if it meets the safety metrics for the specific application. When we look at trusted security, we have a nice bunch of customers, but these customers are really our adversaries, and they are not interested into the normal use case. They don't care about the normal use case. They are looking at crazy use cases that can be leveraged to, for example, extract secret information. So this is really a completely different problem. Looking for doing cost assurance security verification than doing regular functional.
So I didn't got to.
So one problem with hardware, you can have, let's say, security vulnerabilities that are there because you didn't think about it. Think about meltdown spec. They do some crazy use of cache, and things like that, and they leverage this. But you could also have maliciously inserted vulnerabilities. And this is a taxonomy of hardware Trojans from Trust Hub. And really, a Trojans has two main aspects. A trigger, so normally a Trojans would only trigger in very rare condition. When your IC is operating normally, it's there, stealth mode. When the attacker wants to leverage the Trojan, it can send whatever rare condition required to trigger it. And then once it's triggered, you deliver a damaging payload. So if we look at this taxonomy, we can see there are many aspects of hardware Trojans. The insertion phase, you could even have in the specification, design, you would have some ambiguities in the specification on purpose. Fabrication, of course. The abstraction level, you could insert it at gate level, layout, physical level, RTL level. What's the activation mechanism? What's the effect? Leaking information, degradation of performances, where it is located, and physical characteristics. This is one way. This is, a new word, I would say, and this is, I think, a first attempt to kind of agree on certain names and characteristics. And again, this is taken from Trust Hub. You can Google it. So if we look at the IC development steps, as we said, you can have malicious insertion in all the steps. Okay. From one spin point of view, we look at these steps. For example, we do not have technology to detect insertions done, for example, in the GDS2. Again, it's a huge problem. Obviously, we don't cover all of it. We cover a portion of it, which is really this part. So what we really need is a new technology, new methodology to do trust assessment, to do trust measurement, what metrics, how can we define a metric to define trust? Because you might have different applications where you can have different dollars attached, to how much trust assurance you can achieve according to your budget, according to your application. So you need the way to measure trust, and you need new solutions. And again, Trojans are not functional bugs. They are deliberately inserted stealth mode function. If you look at functional verification, you're gonna miss bugs in the things you look for, some crazy corner case. Never mind for the things you don't look for, okay? So for example, you could do some code review. This is actually used, but if you have seen any complex IP today, you get an IP which is fairly complex. You can be a very experienced designer, lot of experience, but if you haven't never seen that IP before, which has a lot of performance optimization, crazy things, lots of configuration, if it's something obvious, you might find it. But if it's a smartly inserted Trojans, you have basically no chance to find it with the code review. So at OneSpin, we have different technology to face this problem. One is automatic trust assurance. We basically, have technology where we get the design. We have some script to run the tool, and we pop out a trust assessment report. And also we have debug capabilities if you want to drill into some specific issues. So these are just some examples where we've been running this. There are examples from TrustHub, which has like a test bench of designs with Trojans inserted in them. You can get examples from conference papers. There are lots of conference papers where they demonstrate sometimes how simple thing you can do and mess up the whole chip. And so from there, we can also derive example. And we also generate our own design with Trojan inserted. If we look at the triggers, you could have very simple trigger where you just have a specific input value that trigger the Trojans. You can have a large counter. You can have arbitrary complex trigger where you might need a very complex sequence of things to trigger the Trojan. And you can really distribute this into the normal logic of the circuit. And it's not like you have a separate process that triggers the Trojan. That would be easy to spot. You can distribute the Trojan in a way that it kind of melts into the normal functionality. And of course, you can have all sorts of different payloads, secret leaking, data corruption, and so on and so forth. What's under the hood? Of course, Formal has a big role into detection of vulnerabilities and Trojan because it's the only technology that can prove the absence of certain behaviors. But you also need some intelligent structural analysis, also to limit the complexity of the formal proofs, to find the relation between different parts of the design that are not obvious. And you also need kind of detection rules that captures, for example, known Trojans, that capture suspicious code patterns, that capture unusual code patterns, that could, be a Trojan. We also have additional technology which is really used to turn specification into executable trusted specification. So with this technology, for example, we have applied it to RISC-V core. I have some results later. And here, the crucial thing is if you can manage to build a trusted executable spec, then you can do some formal equivalence between the trusted executable spec and your actual implementation and make sure they precisely match. This was actually applied to open source RISC-V core from a US defense contractor, Adaptive. This core is, at the moment has a lot of interest in US defense. And we found some bugs, or the solution found some bugs. But apart from the corner case bugs, so by the way, we're talking about the 64-bit core, 5-stage pipeline, with the optimization like branch prediction, instruction replay, verify, taped out. It's not, let's say, a trivial example. It's a real core. And in addition to some crazy corner case bug, for example, one thing the solution found was a seize instruction, which is a non-standard instruction that was not undocumented. It was there, not documented. Basically, only the design knew about it. And it's like, what's this for? I'm not suggesting this was maliciously inserted, but it doesn't matter. The point is, this solution, can reveal things. Not only corner case bugs, let's say, ensure that the hardware does what it's supposed to do, but also reveal things that where the hardware is doing something that it's not supposed to do. And that's the crucial aspect of trust. So this was quite an interesting finding. So in terms of other parts of the IC development steps, for example, when you generate netlist through your tool, if you have a trusted RTL, you can use formal equivalency checking to, for example, prove that the netlist precisely match the RTL, and you then can say, okay, I trust this netlist. Similarly, if you go from a synthesis netlist to a place and route netlist, you can use a CFPGA equivalency checking for ensuring that the PNR netlist is a precise match and no malicious intervention has been done, whether into the netlist itself or into the script that generates the netlist. So this might seem an obvious thing for ASIC guys, because ASIC project, they always run equivalency checking before tape out, but not in FPGA. And OneSpin has dedicated equivalent checking technology for FPGA flows. In FPGA, still a lot of people, which amazes me, for whatever reason, if you look, for example, in avionics, they move slow and they still use a lot of gate level simulation. And if you start using advanced optimization in your FPGA, you really run into the risk of some problem, and this problem are not very likely to be detected by gate level simulation. Apart, the gate level simulation is slow and painful. But yeah, so in apart this, let's say, catching issue with synthesis in FPGA, also this is important doing equivalency checking to make sure that there has not been any malicious insertion. Yeah, 2 minutes, yeah. So if we look at the taxonomy again, this is like a quick view of what we cover. As you can see, we don't cover everything, particularly when you go into the physical stuff, the actual production step, but we do cover a lot of issues with the hardware Trojans. And if you want to know more, you can go to the OneSpin website. I wrote the blog also on this, and we have also a paper on the RISC-V verification with the adaptive that was presented in US in this conference, and we just got permission from the conference because in the past it was restricted distribution to US agencies and US defense contractors. Now it's we got permission to distribute to whoever we want, so that's good. And I think that's all. Any question? Maybe I have 1 minute for question, no? Yeah.
Dennis Nicholl from Southampton. I wanted to ask whether how well you can deal, or whether you have any way to deal with what might be called hostile place and route. In the place and route stage, one could easily design in fairly substantial power line fluctuations that could be side channel analyzed, or design in jitter on insecure ports, which could then be read externally but wouldn't show up in the functional verification.
We don't detect those. Yeah. So as long as there is a change in the functionality, but if you do this kind of stuff, we don't detect those. Yeah. So, well, if it's truly redundant, you should be able to prove that it's redundant, that it has no effect into the functionality. If it has an effect, it can be found. I mean, of course, it depends whether if you're using the automated trust assurance solution, or if you're using the trust absence, Trojan absence proof, which are two different approaches depending how much critical is the IP for you. But yeah, you can find it, because in a sense that's not truly redundant. At some point it has a role, so at some point it's going to come in and play a role. Yeah. Sure. Sure. You're right. Sure. So that's correct. So this is a different problem. We also have technology for that kind of problem. One thing is looking for malicious insertion, Trojans. One thing is looking for security vulnerabilities that are not malicious. It's a different problem, like meltdown, for example. And there are also solutions for those. And they are, in a sense, two different things. Ultimately, it's a vulnerability, but they have a different DNA and they need different technology to be found. Thank you.